My name is Hardik Singh, and I'm a product manager at HEBI Robotics. This video is about trajectories and trajectory generation. An earlier video has already covered the theory behind trajectories. If you're interested in learning about that, I recommend you go check that video out elsewhere in the playlist. For this video, we will have a really quick review as to what a trajectory is, why using trajectories can help you and be beneficial for motion control, and the majority of this video will be focused on live action demos where we take a look at trajectories on a real live robot. What is a trajectory? Putting this long definition aside, a trajectory is essentially just a set of positions, velocities, and accelerations which are matched up with an array of times. And what this does is that per unit time, your robot can be given a command which is designed to, with certain constraints, to make sure that it knows where to be and how fast to be moving through time. Why use trajectories? They can be very, very useful when used correctly. It is important to command smooth and feasible motions to move from one pose in your robot to another. And if you were to not use trajectories, that would you would simply be commanding for, let's say, positions, and you would notice that this motion would be neither smooth nor feasible. You can design trajectories to make robots move more similarly to humans, and a proper trajectory generator will make sure to take in a lot of different constraints depending on the given use case. You can check for and prevent failure modes as you put your trajectories together. This is something we'll see later in this video as the difference between not using trajectories and using trajectories. And finally, when it comes to good motion control, tuning your control gains is not enough by itself. You can improve the behavior of your motion control significantly by using trajectories. And this is another thing you'll see in the live action demos. But enough of that, let's get started with playing with a real robot. Ultimately, using trajectories is all about getting the desired motion control that you want for your robot. In this case, I will be demonstrating this with a 6 degree of freedom arm, where there are 6 actuators, each representing a singular degree of freedom. I'm going to start off by showing how trajectories can make a difference even for a single degree of freedom, for a single joint in this case. And I'll later even show what that looks like on a full arm system level scale. So let's actually start off by focusing in this case on what we call wrist 2. So on screen, you will see that there's a graph that's actively plotting right now for wrist 2, and that's this wrist over here. So it's the second from last joint in the chain from the base to the end effector. As I move this around, you can see that this is the degree of freedom that I'll be playing with. And I want to show how simply tuning gains, simply tuning the control strategy at a joint level isn't always enough to get the desired motion control that you want. What I'll do here is that I'm going to command just position values for this joint. On the graph, the continuous line will show the feedback and the response of that hardware to my commands. And the dotted line that you'll see in a second will be the commands that I am sending. So if I abruptly set a commanded position, you'll see how the dotted lines show those abrupt, nearly step-like commands being sent for position. The feedback, as it's the continuous line is the feedback, which is trying to keep up with those commands. And what it's doing is trying to get there as fast as possible, and at the end, smoothing out the motion of the actuator. And that's actually coded into our firmware, so that's already happening. But that comes down to our control strategy. So our control strategy is making sure that when a position is commanded, we're going to approach that position and smoothen out the profile of our motion a little bit. But what we're seeing here is that if I wanted to get smooth motion for this arm, for this joint, this degree of freedom, I'm not getting that by commanding just position values. How I can get it, however, using trajectories. So what I'm going to do now instead is run a little bit of code that's going to allow me to teach this arm a few positions. So we were just moving this degree of freedom back and forth, right? So I'll do the same here with the trajectories. I'll set one waypoint right here. And I'll turn this around, and I'll set another waypoint right here. Now, I will set these waypoints to run by themselves. And I really want you to take a look at, firstly, how this motion is a lot more in control. That's one thing. But on the graph, you're seeing that the feedback, the continuous line, the ability of the actuator to stay on track to the motion that we want is much, much better when we've created a trajectory from the desired positions. I haven't done anything else other than still set positions, but in this case, the positions are being fed into a trajectory generator that creates velocity, acceleration, and position profiles for the actuator to follow. So in this case, the control gains become a lot more powerful because they allow the actuator to actually follow the desired motion profile. That is invaluable when you're trying to get the motion control that you want. And the previous jerky motion without trajectories make it possible for this for the hardware to either damage itself or damage the surroundings. Using this trajectory, we're in a lot more control of what we want to see, and the motions are a lot more predictable. Yes, it's a little bit of computational power, but the trade-off is that you get far better motion and motion control. Finally, I can show this for the entire system. So I'm going to run this same code again. But this time, I'm not going to restrict it to just one joint. In another video, we talk about how there are benefits of joint level control. And here we're going to see those benefits in action, even though you can head over to that video to learn about those benefits. We are creating that same trajectory profile for each and every one of these joints at an individual level. And that allows us to get far smoother motion. And again, far more predictable motion. So let's actually just see that in action. I'm going to set a position out here. And I'm going to set a position over here. And I'm going to set a position over here. They're far from each other, but it doesn't matter how far they are. With our trajectory generator, we can make sure that we follow through those positions and get the desired motion that we want. Another thing I should note here is that you can really tune gains as much as you want, but you want to be tuning gains to your specific motion. I can't tune an arm beforehand and then suddenly feed it proper trajectories and expect it to be smooth behavior, because the control gains and the ability of the arm to follow a given trajectory comes after you've commanded that trajectory. Another thing is that tuning gains alone, as I mentioned earlier, is never enough. And in this case, what we're doing is we're commanding minimum jerk trajectories, where jerk is actually the time derivative of acceleration. So in this case, the trajectory matches velocity and acceleration constraints at the end of each waypoint. And so it prevents the arm from jerking into any position. And it really gives it a smoother profile, sliding into each position, sliding out of each waypoint. At the end of the day, the better your input that is used to create the trajectory, the better your trajectory will be. But doing trajectories all around the arm really allow you to make the most of your motion control. As a final note, what I will emphasize here is that what we are doing is not restricted to just robotic arms. The concept of trajectory generation and trajectory planning, it has to do with simply how to get from one point to the next with a given hardware, with given actuators, with given motors and embedded systems like this. Whatever configuration you use, these principles still remain just as useful. So whether you're doing this for a mobile base that's moving around, you're going to be wanting to create trajectories for those individual wheels so as to prevent your mobile base from just suddenly moving around, but instead creating a smooth velocity, acceleration, and position profile. Lastly, this is not, again, what's not limited to standard robotics also. Think of a legged robot that still has the same requirements of creating that smooth motion with each step, and so a trajectory generation will once again prove invaluable. In a metaphorical sense, you can think of what's happening here as an orchestra conductor conducting his orchestra. So he's really telling each part of his orchestra, each part of his system, to speed up, to slow down, to move in accordance with each other and in accordance with smooth, controlled, ideal behavior. The process of generating trajectories is really powerful, and we highly recommend you take a look at making sure you do that for your robotic applications. But this has been a quick demo into why trajectory generation is so much more valuable than simply commanding a given position, velocity, or acceleration command.